Hello everyone. Good evening to all. How are you? Hello everyone. Good evening to all. How are you? Okay. So guys, it's time to start your class. I'm launching the technical polls. Just respond there whether my voice is clearly audible or not and my screen is visible clearly or not. Everyone, please respond to the polls. Whether my voice is clearly audible to you or not, and also my screen is visible clearly or not. Yeah, I hope everything is good. So we'll start our class. Sure. Okay, so it's our fourth lecture of complex number. Okay, and in the previous class, already I told you about the argument and also about the polar form of a complex number. Okay, so I'm asking you first, if z is a complex number which is x plus iy, okay, and argument of z is theta, then can you tell me what is the polar form of this complex number? Yeah. If z is equal to x plus iy and the argument of this complex number is theta, then can you express this complex number in polar form? Anyone can answer it? Yes, that is actually z is equal to r cos theta plus ir sin theta. Is it or not? So this is the actual polar form of this complex number. So what is r here? Anyone can say what is r? R is actually my mod of z or modulus of z, modulus of the complex number. So this is the polar form of a complex number. Is it or not? So now we'll study in this session some properties of conjugate and modulus and argument. With that, we'll see another form of complex number, that is Euler's form of complex number. Okay, so what is Euler's form of the complex number? Now we see. Suppose z is a complex number which is x plus iy and its polar form. Suppose its polar form is given as r cos theta plus ir sin theta. Okay. Suppose you have a complex number z is equal to x plus iy, and a polar form of this complex number is r cos theta plus ir sin theta. Is that clear to everyone? Then the Euler's form will be, what is the Euler's form? Okay, Euler's form of this complex number will be z is equal to r into e to the power I theta, where r is equal to mod z and argument is my theta. So this is called my polar form. You can ask, sir, how we can get this Euler's form? Okay, if you know the theta and modulus, argument and modulus of that complex number, easily you can express in the Euler's form also. Okay, so remember the Euler's form of the complex number is equal to r into e to the power I theta. So I think all of you needs the derivation of this formula, but it's very easy. You can put here in r cos theta, r into cos theta plus I sin theta. If you'll put the expansion of cos theta and sin theta, finally you will get r into e to the power I theta. You know, expansion of cos theta and sin theta. If you'll put the expansion of in place of cos theta, if you'll put the expansion, and in place of sin theta, if you'll put the expansion of both, then you will get the Euler's form, that is r into e to the power I theta. So what is the series you will get? That is e to the expansion of e to the power I theta you will get. Is that clear to everyone? So remember, no need to go through the derivation of the formula. Just remember, if the argument of the complex number is theta and the modulus of that complex number is r, then we can say the Euler's form of this complex number will be z is equal to r into e to the power I theta. Is that clear to everyone, guys? Yes, tell me. Clear? So simply now if and remember, e to the power I theta is equal to, actually e to the power I theta is equal to, can be expressed as cos theta plus I sin theta. So if you'll put here the expansion of cos theta, and if you'll put here the expansion of sin theta, then you will get the series which represents to e to the power I theta, which is the series will be the expansion of e to the power I theta. Remember, e to the power I theta is equal to cos theta plus I sin theta, and r into e to the power I theta is r into cos theta plus ir sin theta. Clear, beta? Yes. Clear? So what is the modulus here? If the complex number is given in the form of Euler's form, then what is the modulus of this complex number? Already I told you. You can message in the chat box, beta. Jaldi se batao. What is the modulus? R is my modulus. Yes or no? What is the argument? Theta is my argument. Simple. If any complex number is given in the form of Euler's form, then R will be the modulus and argument will be the theta. Then what is the conjugate of this complex number? What is the conjugate? What is the conjugate of this complex number? Conjugate will be r into e to the power minus I theta. Okay, r into e to the power minus I theta will be the conjugate of z is equal to r into e to the power minus I theta. Okay, clear everyone? If z is equal to this, then z bar will be this. Remember, this is the Euler's form of the complex number. Okay. Okay. Now, all of you know, already I told you cos theta plus I sin theta. It's actually called Euler's identity. Remember, it's called actually, what is that? Euler's identity. So cos theta plus I sin theta. If you'll put the expansion of cos theta here plus I into, if you'll put the expansion of sin theta here, then I will get the expansion of e to the power I theta. So remember, this is called my Euler's identity. Is that clear? Okay, if I'll ask you if theta is equal to pi, then can you express in the the exponential form or Euler's identity? Can you use for it? Yes, we can use it simply. Cos of pi plus I sin of pi. Okay, cos of pi plus I sin of pi, which is equal to e to the power I pi. So what is the value of e to the power I pi? If I'll ask you to find the value of e to the power I pi, then we will do this calculation. So cos pi is cos pi. What is the value of cos pi? That is -1. Yes or no? And sin pi is 1. So -1 plus I, is it? Sin pi is 1. No. Sin pi is 0. Yes or no? So this becomes 0. So this is equal to e to the power I pi. The value of e to the power I pi is equal to -1. And value of e to the power I pi is -1. Remember, e to the power I pi is equal to -1 and e to the power I pi plus 1 is equal to 0. This is the identity. Okay, when theta is equal to pi. Clear, everyone? Okay. Now we'll see polar form versus Euler's form. Okay, so see, r into cos theta plus I sin theta is equal to r into e to the power I theta. Okay, similarly, if I'll take the conjugate r into cos theta minus I sin theta is equal to r into e to the power minus I theta. So from both sides we can cancel r. Yes or no? So this is actually polar. So cos theta plus I sin theta is equal to e to the power I theta, and cos theta minus I sin theta is equal to e to the power minus I theta. Clear, everyone? I hope this is clear to all of you guys. Clear? So we'll solve some questions. First of all, we have less time. So first we'll try to complete all the theories. Then we'll solve some questions on this. Okay. Now we'll start some properties of conjugate. So first property is saying Key Z bar is the mirror image of Z along the real axis. Already we studied many times these things. If you have a complex number Z here, then the mirror image will be Z bar. Yes or no? Then the mirror image will be Z bar on the real axis. This is my real axis. So remember, always the conjugate of a complex number is the mirror image of the complex number along the real axis. Clear? Similarly, the second property is saying conjugate of Z is Z. Okay, conjugate of Z is Z. Okay, let's prove it. So let Z is equal to X plus IY. Then conjugate of Z will be X minus IY. Then conjugate of Z will be X plus IY again, and which is equal to Z. So remember, this is important. Conjugate of Z or Z bar, conjugate of Z is Z itself. Okay, clear? This is the second property of conjugate of a complex number. Come to the third one. What is it? What it's saying? Achha, if Z is equal to Z bar, then Z is purely real. Is it? How? Okay, suppose I'm taking Z is equal to a pure real number, suppose a plus 0I. Okay, so can I say Z bar is also a that same number? So Z bar will be a minus 0I. So you can see here Z bar is equal to Z here. I'm getting Z bar is equal to Z. That means Z is purely real. So this is equal to A. Z is equal to A. Just we are writing it is in the form of A plus 0I, A minus 0I. Both are same. So Z bar is equal to Z when the Z is purely real number. Yes, I hope this is clear to all of you guys. Okay, similarly, in the next thing we'll see Z is equal to conjugate of minus Z, minus of conjugate of Z. Okay, then Z is purely imaginary. Okay, just I'm taking right hand side. Z is equal to purely imaginary. Suppose I'm taking 0 plus Bi. Right. So Z bar will be 0 minus Bi. Yes or no? Okay. So you can see here, if you add these two complex numbers, Z plus Z bar. Okay, Z plus Z bar. What you are getting? 0 you are getting or not? That means from here we can prove Z is equal to minus of Z bar when the number is, or the complex number Z is purely imaginary. Remember, when the Z is purely real, then we can say conjugate of Z is equal to Z. But when Z is purely imaginary, we can say Z is equal to minus of conjugate of Z. Clear, everyone? These are my 4 properties we have covered till now. Okay, let's move to the next property. Yeah. Let's move to the next property. What is that? Oh. So properties of conjugate, it's saying कि conjugate of Z1 plus Z2 is equal to Z conjugate of Z1 plus conjugate of Z2. You can prove by taking Z1 is equal to X1 plus IY1 and Z2 is equal to X2 plus IY2. Easily you can prove it. Okay. So remember, conjugate of Z1 plus Z2 is equal to conjugate of Z1 plus conjugate of Z2. Okay. So you can take now. Let I'm taking Z1 is equal to X plus IY. Z2 is equal to X1 plus IY1, X2 plus IY2. Now if you'll try to find Z1 bar plus Z2 bar. So what we will get? X1 minus IY1 plus X2 minus IY2. Right? So see here, this is my right hand side I'm getting. Okay, if I'll individually add both the complex number, then what I am getting? X1 plus IY1, that is left hand side. Z1 plus Z2 I am trying to getting Z1 plus Z2, that is X1 plus IY1 plus X2 plus IY2. From here I can say, okay, X1 plus X2 minus I into, sorry, plus y1 plus y2. Okay, so this is my complex number z1 plus z2. Now if I take the conjugate of the complex number, then this will be x1 plus x2 minus I into y1 plus y2. Is it or not? Tell me, is it proved or not? Okay, so similarly you can prove the sixth property also, that is conjugate of z1 minus z2 is equal to conjugate of z1 minus conjugate of z2 also. I hope you don't need the proof of this result or property, because already we proved the fifth one, and it's similar. In the similar way you can prove the sixth one also. I hope this is clear to all of you guys. Clear? JNB class 11th, is it clear? Simple. Okay. So let's move to the next property here. We have a lot of properties in conjugate. Okay. So seventh one is saying, sir, that is conjugate of Z1 into Z2 is equal to conjugate of Z1 into conjugate of Z2. So this rule will be applied for addition, subtraction, multiplication, and also for division also. That is, if we take Z1 is equal to x1 plus I1 and Z2 is equal to x2 plus y2, then you can prove this also. So remember, Z1 into Z2, conjugate of Z1 into Z2 is equal to product of individual conjugate of Z1 and Z2. Okay, similarly also the eighth one, that is conjugate of Z1 upon Z2 is equal to conjugate of Z1 upon conjugate of Z2. Clear guys? Chalo, ठीक है? Is it clear? Let's move to the next property. What is that? Saying now real of Z is equal to real of Z bar when is equal to Z plus Z bar by 2. How can you prove it? Okay, I'm taking, suppose Z is equal to x plus iy, then Z bar will be x minus iy. So if we'll take the right hand side, then if we'll add these two, what I'm getting? I'm getting 2x. Only I'm getting 2x. Z plus Z bar I'm getting 2x. Then x is equal to, I'm getting what? X is equal to Z plus Z bar by 2. Yes. So x, what is x? That is real of Z is equal to Z plus Z bar by 2. Okay. Similarly, also we can say real of conjugate of Z. If we'll take conjugate of Z, okay, then also we'll get conjugate. This is also the real of conjugate of Z. Real of Z. Which one is the real of Z? That is also the real of conjugate of Z. This is my real of Z. This is my real of Z. So both are same, na? So in place of real of Z also, I can write real of conjugate of Z. That is also Z plus Z bar is by 2. So it is proved now. It's proved now. Simple enough. Yes. So in the similar way, we can see, we can prove also the 11th property, that is imaginary part of Z is equal to Z minus Z bar by 2 iota. Okay. You can prove it easily. Okay. Done. Shall I move to the next thing? Last property we have now, and the important one also. Chalo, let's prove it. Okay. So what is that? Z1 into conjugate of Z2 plus Z2 into conjugate of Z1 is equal to 2 into real of Z1 into conjugate of Z2 is equal to 2 into real of Z1 conjugate of Z1 into conjugate of Z2. Okay. So I'm taking the left hand side first. So Z1 into Z2 bar plus Z2 into Z1 bar. Okay. So if we'll take, so this can be written as also Z1 into Z2 bar plus conjugate of Z2 Z1 bar. Can I write? Oh, sorry. Z2 bar into Z1 bar. Can I write this? Because we know na, Z2 conjugate of Z2 is equal to also again Z2. So this expression and this expression is same. Yes or no? I can write or not. So now Z3. Okay, one thing. What we did? Okay, if we take this as my one complex number and this is another complex number, sorry, they both are same now. If this is my, suppose I am taking let Z3 is equal to Z1 into Z2 bar. Okay, then also it is equal to Z2 bar into Z1, same na? So we can write this as, if we take this complex number as Z3 plus, then it will be conjugate of Z3. Yes or no? So we know already. Already we studied this property na. Z1 plus Z1 plus Z1 bar is equal to 2 into real of Z1. So here we can say 2 into real of Z3. Remember Z plus Z bar. Already I told you that Z plus Z bar is 2 into real of Z. This property. This from here we can say Z plus Z bar is equal to 2 into real of Z na. 2 into real of conjugate of Z, also we can say 2 into real of Z also. Hai. So by using the same property we can say here Z plus Z bar is equal to 2 into, we know since Z plus Z bar is equal to 2 into real of Z, then we can write here also 2 into real of Z3, and also it can be written as 2 into real of Z3 bar. Okay, so in place of Z3 we can write 2 into real of Z1 into Z2 bar, and also 2 into real of Z1 bar into Z2. This is also proof. This is an important property. Remember, Z1 into Z2 bar plus Z2 into Z1 bar is equal to 2 into real of Z1 into Z2 bar, which is also equal to 2 into real of Z1 bar into Z2. Is that clear to all, guys? Let me know if it is clear to all of you guys. Clear? Okay, we are done with all the properties of conjugate of complex number. So what are those we studied? Let's revise all those properties. First is this: Z bar is the mirror image of Z in the real axis, and also conjugate of Z is equal to Z. Remember, these properties will be help a lot in the problem solving. Okay, so if Z is purely real, then we can say Z is equal to Z. And if Z is purely imaginary, we can say Z is equal to negative of conjugate of Z. Here, okay. Fifth, these things we have covered. Okay, 6 and 7, 7th, 8, 9 to 9 is missing. Okay, let's see. 10. This is already we discussed, and the last one is this. Okay. Now we'll move through the properties of modulus. Properties of modulus of a complex number. Right. So let's solve one question first. I'm giving you one question. If a plus ib to the power 5 is equal to alpha plus I beta, then b plus I a to the power 5 is equal to which of the following? First option is beta plus I alpha. Second option is alpha minus I beta. Third option is beta minus I alpha. And last option is minus alpha minus I beta. So I'm giving you 1 minute for this question. Try to solve it, guys. And your time starts now. Try to solve it. And I'm launching the poll also. Just respond in the polls. Which option is correct? Option A is correct. Wow, very good. Yes. So all of you have answered the question, and it's correct actually. So how can you solve it? You need to solve me, or we'll go through the next thing. We'll solve it. Okay, let's solve. So it is given that a plus I beta, sorry, a plus IB whole to the power 5 is equal to alpha plus I beta. So can I write this as AI minus B by I whole to the power 5 is equal to alpha plus I beta? Can I write this? Yes or no? Because if you'll divide I, okay, so what will happen? If you'll open this bracket, if you'll open this bracket, what you will get? AI upon I, which is A, and B upon I, which is plus IB. Yes or no? So the same expression can be expressed as like this. Okay, now what we will do, we'll write this as minus B plus IA whole to the power 5 is equal to I alpha minus beta. If you cross multiply here, okay, so this will be I into I beta and I to the into I alpha. That is I alpha minus beta. Yes or no? Clear? Okay. Now, if we'll solve it again, or if we'll try this, we'll take from this bracket. If we'll take minus 1 as common, so what will happen? Minus 1 to the power 5. This becomes B. This becomes B minus AI whole to the power 5, which is equal to I alpha plus beta. Now, if we'll multiply minus on both sides, what we'll get? So this will become B minus AI to the power 5 is equal to, this becomes minus I alpha, or what? This is plus, no? Sorry. This becomes beta minus I alpha, right? Now, if we take conjugate on both sides, what will happen? If we take conjugate on both sides, then it becomes B plus AI to the power 5, which is equal to beta plus I alpha. This is your answer, beta plus I alpha. So what is the correct option? Beta plus I alpha, which is the first option, is the correct. Okay, first option is the correct answer. Okay, so now let's move to the next thing, properties of modulus. Okay, see here, real of Z is less than equal to mod Z, and also imaginary of Z is less than equal to mod Z. How? Is it true or not? Yes. So if I am taking Z is equal to X plus IY, suppose I am taking Z is equal to X plus IY. So that means if we plot this in the organ plane, this is Z, which is equal to X plus IY. If we join through the origin and if we drop a perpendicular from here, so this length will be X and this length will be Y. Okay. So can you say, this is my mod Z, OP is my mod Z. Okay. OP is my mod Z. So mod Z is greater than, what is real of X, real of Z? So real of Z is X. Yes or no? And imaginary of Z is Y. So from here, from this figure, we can observe mod Z is greater than equal to real of Z, X, real of Z, and also mod Z is greater than equal to imaginary of Z. Is it or not? Everyone, is it or not? Clear? Is it clear to everyone, guys? Let's respond in the chat box if it is clear to all. Everyone, you guys also, you can respond in the chat box. So using the similar process, you can use the similar whole process to prove this property. So what is the second property saying? Real of Z is greater than equal to negative of mod Z. The imaginary of Z is greater than equal to negative of Z. Yes, obviously. Yes, sir. So real of Z is greater than equal to negative of mod z and imaginary of z is negative of. Okay, chalo, ye ho gaya. Then properties of third property, what it is saying, so mod z is equal to modulus of minus z. Okay, let's see. This we need to prove. This is true or not. So if I am taking z as my x plus iy, okay, then minus of z will be minus x minus iy. Then conjugate of z will be x minus iy. Then negative of conjugate of z is minus x plus iy. So in all the cases, in all these cases, I am getting 4 complex numbers. Yes or no? 4 complex numbers. So if you try to find mod z, what it will be giving you, that is under root of x square plus y square. So if you try to find the mod of negative of z, okay, modulus of negative z, then it will be also giving you minus x square plus minus y square, which is also equal to under root of x square plus y square. Similarly, if you try to find modulus of conjugate of z, here also you will get x square plus minus y square, that is also plus y square. Similarly, modulus of negative of conjugate of z, which is also giving you x square plus y square. That means in all these cases, the modulus is same. In all the for all these 4 complex number, modulus is same always. Remember, it is important. Clear? It is clear to all. Let's move to the next property. What is it saying? Oh, this is nice. Z into Z bar is equal to mod Z square. Is it or not? Can we check it? Okay. So let I am taking Z is equal to x plus iy, and mod Z I am taking conjugate of Z is x minus iy. So if you multiply both the complex number, what we are getting? Let's multiply z into conjugate of z, that is x plus iy into x minus iy. So a plus b into a minus b, that is x square minus iy square, which is equal to x square. I square is -1, so minus minus will be plus, x square plus x square. So this is actually same as mod z square. Okay. So what is mod z here? Modulus of z I am getting on root of x square plus x square. So square of modulus of z is on root of x square plus y square whole square. Then modulus square of modulus of z becomes x square plus y square. So see here we are taking the left hand side, and this is my right hand side. From here we can observe we have proved this property. Hence we are getting LHS is equal to HS, and it is proved. Yes or no? So remember, Z into conjugate of Z gives you always mod square of modulus of Z. Here square of modulus of Z. Clear everyone? JNB Pune, it is clear? Yes or no? Guys, please respond to the chat box. If it is clear, let's move to the next property. What it is saying? Modulus of Z1 into Z2 is equal to modulus of Z1 into modulus of Z2. Is it true? Yes, it is true. Okay, we can check it also by using you can take Z1 is equal to x1 plus iy1 and Z2 is equal to x2 plus iy2. Then you will get modulus of Z1 into Z2 is equal to individual modulus of Z1 into Z. You will get. So in general we can say modulus of Z1 into Z2 into Z3 up to Zn. Okay, modulus of Z1 from Z1 to Zn, product of Z1 to Zn is equal to individual modulus of each of the complex number. Product of individual modulus of each of the complex number. Okay, in generally we can say kitne bhi number, in how much number you have, complex numbers you have, if there is in this form, that means suppose Z1 into Z2 into Z3 into Z4 hai, then you can write this as modulus of Z1 into modulus of Z2 into modulus of Z3 into modulus of Z4, right? Clear? Similarly also here, जैसे भी likewise we have already discussed in conjugate. Similarly, you can here also discuss this modulus of Z1 upon Z2 is equal to modulus of Z1 upon modulus of Z2. Okay, so another property I would like to say here, that is modulus of Z to the power n can be written as modulus of Z into modulus of Z into Z into Z up to Z, n times Z. This can be also written as modulus of Z into modulus of Z into modulus of Z up to. Okay, so these are the three properties important here. You can remember these things. Okay, no need to remember. If you understand these things once, then it will be easy to you. Right? Am I correct or not? Yeah. So let's move to the next thing. The seventh property, what it is saying. Remember, this is important. It is useful also. Right? So it is saying that square of modulus of Z1 plus Z2 is equal to mod Z1 square plus mod Z2 square plus 2 into real of Z1 into Z2 bar. So don't think like that. Z1 plus modulus of Z1 plus Z2 is equal to modulus of Z1 plus modulus of Z2. It is not equal. Okay, it's not true actually. It is not true. Modulus of Z1 जैसे conjugate में हम लोग पढ़े थे, Z1 conjugate of Z1 into Z2 is equal to, it can be expressed as conjugate of Z1 into conjugate of Z2. But in the case of modulus, it can't be 1. Okay, remember. Okay, so how can you prove this? Okay, so if you take the left hand side, I'm taking the left hand side, which is modulus Z1 plus Z2 square. Okay, so we know another property, since Z into Z bar gives you mod Z square. So since reversely we can express this form, we can write mod Z square is equal to Z into Z bar. So similarly here also we can write Z1 plus Z2 into conjugate of Z1 plus Z2. We can use this property and write, yes, and again use the properties of conjugate here. We can write Z1 plus Z2 is equal to conjugate of Z1 plus conjugate of Z2 also we can write or not. Yes or no? So if we'll multiply here, what you will get? See here. So Z1 into Z1 bar plus Z1 into Z2 bar plus Z2 into Z1 bar plus Z2 into Z2 bar. Sorry. We know Z, by using this property also, we can write here, this becomes Z1 mod Z1 square and this becomes mod Z2 square. And we know already, that is Z1 into Z2 bar plus Z2 bar into Z1 bar is equal to 2 into real of Z1 bar into Z2 or 2 into real of Z2 bar into Z1. Already we studied these things. So here in this place we can write this as 2 into real of Z1 into Z2 bar, we can write or not. So this is proved now. This is equal to right answer. And it is proved. You can see here. If you have any doubt, you can ask. If you have any doubt, you can ask. Clear, everyone? Guys, is it clear to all? Yes or no? Genevieve Pune, can you respond in the chat box? Clear? Okay. So let's move to the next property. You can use a similar last process, previous process or approach. You can prove this also. So remember, this property is also true. By using this process, you can prove this property also. Yes or no? So remember, just remember this property. So in place of plus, here minus becomes. Okay. In the last property, we have plus sign, and in this property, we have minus sign. Instead of plus, we have taken minus only. Right? Clear, guys? Okay. If it is clear to all, then we'll move through the properties of argument now. Chalo, let's move to the properties of argument. Okay. So first property is saying argument of a complex number is 0 is not defined. Already we discussed this. Okay. So argument of a complex number 0 is not defined because 0 plus 0. Suppose this is my complex number. It represents to a point only. It represents to a point only. And point, this point has a lot of directions. Okay. So the argument can't be defined because this can be its direction, this can be its direction, this can be its direction, this can be its direction. So what is the angle you can define? We can define the argument here, but it is defined by the magnitude. Magnitude is 0, right? 0 is the only complex number whose magnitude is not, which argument is not defined. Clear? Okay. Come to the second property. What it is saying? If Z is purely real, okay, if Z is purely real, then argument of Z is equal to 0 or pi. Okay. Similarly, you can visualize easily here also. Suppose a complex number Z1 lying here. So what is the argument of this complex number Z1? That means, what is the angle made by this complex number Z1 with the positive x-axis? So here in this case, argument of Z1 is 0. Yes or no? So the angle made by the complex number Z1 with the positive x-axis is 0. That means argument of Z1 becomes 0. Is that clear to everyone? Similarly, if we take another complex number here, suppose I'm taking Z2 here. Okay, Z2 here. Now can you tell me what is the argument of Z2? What is the argument of Z2? The angle made by the complex number Z2 with positive x-axis, that is pi. So argument of Z2 is pi. Okay. So when Z is purely real, that means Z is purely real means Z is lying on the real axis. Is it or not? When the complex number lying on the real axis, then the argument may be 0, it may be pi. It can be 0 or pi. Nothing else. Understood? Everyone? Clear? Shall I move to the next property? Okay. Chalo. If Z is purely imaginary, okay. If Z is purely imaginary, suppose I am taking here. So Z is purely imaginary means suppose I am taking here my Z1. So then what is the argument of Z1? What is the angle made by the Z1? Made by Z1 with positive x-axis, that is pi by 2. So argument of Z1 is pi by 2. So if the complex number lying on the negative imaginary axis, suppose this is my Z2. So what is the angle made by the complex number Z2 with positive x-axis? That is argument of Z2 becomes minus pi by 2. So remember, when Z is purely imaginary, argument of the complex number is plus or minus pi by 2. And when it is purely real, the argument is 0 or pi. Okay. When it is purely imaginary, the argument is plus or minus. Clear, everyone? Clear? Crystal and clear? Let me know in the chat box, everyone, guys. It is clear? Okay. So let's move to the next property. What it is saying? Oh, this is important. Huh? This is important. Try to understand. Okay. So what I'm saying, argument of Z1 into Z2 is equal to argument of Z1 plus argument of Z2 plus 2m pi for some integer m. Okay. So how can you prove this property? Okay. So let's I'm taking let my Z1 is R1 into e to the power I theta 1. Okay, and Z2 is I'm taking those complex number in Euler's form. Okay, no issues, na? It is in the Euler's form. I'm taking Z1 is equal to R1 into e to the power I theta 1, which is a complex number, and Z2 is R2 into e to the power I theta. Okay, so if you multiply these two, Z1 into Z2, so what you are getting? R1 into e to the power I theta 1 into R2 into e to the power I theta 2 you are getting. Yes or no? So finally what I am getting, R1 into R2 is into e to the power I into theta 1 plus theta. Yes or no? So now this is the complex number Z1 into Z2. This is again a complex number, na? Which modulus is R1 into R2 and which argument is theta 1 and plus theta 2. So can I say here the argument of Z1 into Z2? What is the argument of Z1 into Z2 you are getting here? That is theta 1 plus theta. Yes or no? So in place of theta 1, can I write this as argument of Z1? Yes or no? Yes. And in place of theta 2, can I write argument of Z2? Yes or no? So simply we can say the argument of Z1 into Z2 is equal to argument of Z1 plus argument of Z2. Is it or not? Yes. Oh, this is proved. Huh? This is easy. Clear or not? Okay. You can ask now, sir, why we are adding this 2m pi? Why we are adding this 2m pi? There is a reason. Huh? There is a reason. That's why we are adding 2m pi. Huh? Yes. What is the reason? Anyone can say? What is the reason why we are adding 2m pi? Guys, why we are adding 2m pi? Anyone can say? Because we know na argument is, now you can say argument is multi-valued function. Yes or no? Argument is multi-valued functions. So argument can be unique. Argument can be unique. So if you are getting argument as pi by 6, 2 pi plus 6 also argument, 4 pi plus pi by 6 is also argument, 6 pi plus pi by 6 is also an argument. Yes or no? So that's why we are adding 2m pi. Suppose in a question it can be asked to find the principal argument, then you need to subtract from 2 pi. It may be needed subtract from 2 pi the argument. Yes or no? When because argument is multi-valued function, so if the argument of the complex number is pi by 6 also, then 2 pi plus pi by 6 is also an argument, 4 pi plus pi by 6 is also an argument, 6 pi plus pi by 6 is also argument. If it is asking the principal argument also, pi minus 2 pi minus pi by 6 also an argument. You can say, is it or not? Principal argument. When something is needed or when someone is asking to find the principal argument, then depend on the situation. So you can find the where the argument is lying, where the complex number is lying. Then you can apply the principal argument rule to find the principal argument. If it is lying in the second quadrant, then it will be pi minus alpha. Yes or no? Like that. So argument is a multi-valued function. Argument can be unique. Okay, is that? But principal argument is unique. What is principal argument? Which is lying between minus pi to pi, when minus pi is not included, but pi is included. I already discussed all these things. We have already discussed a lot of things about argument in the last classes. Okay. Okay. So let's move to the next property. What is that? Fifth property. It is saying argument of Z1 upon Z2 is equal to argument of Z1 minus argument of Z2 plus 2n pi. Same method you can use and you can prove this. Z2 is equal to R2 e to the power I theta 2. Then Z1 upon Z2 becomes R1 upon R2 into e to the power I into theta 1 minus theta. Yes or no? So now this is my modulus, this is my argument. So argument of Z1 upon Z2 is equal to theta 1 minus theta 2. So from here, in place of theta 1, we can write argument of Z1, and in place of theta 2, we can write argument of Z2. Yes or no? Yeah. So similarly, we are adding here 2m pi because why we are adding? Because argument is multi-valued function. Clear? Done? Chalo. Let's move to the next property. What is that? Oh, this is the last one also. Argument of Z to the power n. Argument of Z to the power n, which can be expressed as n into argument of Z plus 2mr. Okay. Okay. Chalo. So by using the similar method also you can prove this property. Right, guys? By using the similar method you can prove this property also. Then I'm asking one question on argument. Okay. So what is the question? If Z and omega are two Z and omega are two complex number, okay, and such that it is given that mod of Z omega is equal to 1. It is given that mod of Z omega is equal to 1, and argument of Z minus argument of omega is equal to pi by 2. Then which of the following is correct? It came in 2019 JEE main question. Options are but Z bar into omega is equal to I. Option B is Z into omega bar is equal to minus 1 plus I by root 2. Option C is Z bar into omega is equal to minus I, and option D is Z into omega bar is equal to 1 minus I upon root. So I am launching the poll also here. Yeah, poll has been launched. Respond to the polls. Which of the following is the correct answer? And I'm giving you 1 minute also. Take 1 minute to solve this question. Please respond who is getting the answer. Please respond to the polls. Okay, so it's time. Anyone is getting the answer? You can respond in the chat box also. How can you solve this question? If Z and omega are two complex number, and it is given that mod of Z omega is equal to 1, and also it is given that argument of Z minus argument of Z omega is equal to pi by 2. By using all this information, so which one of the following is correct? So let's solve. It is given that solution. It is given that modulus of z omega is equal to 1. So can I write this as mod z into mod of omega is equal to 1? So we can write also mod omega is equal to 1 upon mod z, and also we can write okay, if modulus of omega is a complex number, if modulus of omega is r, okay, so r is equal to, I can write mod of 1 upon mod of z, sorry, 1 upon mod of z. So similarly we can write here also another thing is given in the question, that is argument of z minus argument of omega is given as pi by 2. So from here we can write argument of z is equal to pi by 2 plus argument of omega, right? So if we'll take argument of omega as theta, so this becomes pi by 2 plus theta. Yes or no? So finally we are getting argument of z is equal to pi by 2 plus theta. So these are two results we are getting now. Okay. So now what is the complex number omega is? If the modulus of that complex number omega is r, okay, and the argument is theta, can we express in the Euler's form? Yes, r into e to the power I theta. You can write or not. So similarly z will be, from here we can write mod z is equal to 1 upon r. So radius, the modulus of z is 1 upon r. So it can be expressed also 1 by r into e to the power I into pi by 2 plus theta, because argument of z we are getting here pi by 2 plus theta, when theta is the argument of omega. And from this expression here we are getting the modulus of complex number z is 1 upon r. So it can be also expressed in the form of 1 upon Euler's form, 1 upon r into e to the power I into pi by 2 plus theta. Similarly, what is conjugate of z will be, that is 1 by r into e to the power I into pi by 2 minus theta, or okay, yes, minus of, yeah, in this way we can write. Okay, so if z is this, then conjugate of z will be 1 upon r into e to the power I pi by 2 plus theta. Now we'll try to verify which of the following option is correct. Okay, now one is z bar into omega, another is omega bar into z. Okay, so first we'll try to find z bar into omega. So what is that? Z bar into omega, in all the options it is available. No. Yeah. So z bar into omega if we'll try to find. So what is z bar? Z bar is 1 upon r into e to the power minus I into pi by 2 plus theta into omega is r into e to the power I theta. So r will be cancelled out here. So finally what I am having, that is minus I into pi by 2 minus I theta plus I theta. So I theta will be cancelled out. So this will be I to the power e to the power minus I pi by 2. So again it can be expressed in polar form. So what it will be, polar form, by using the Euler's identity. What is that? Since cos theta plus I sin theta is equal to e to the power I theta, and cos theta minus I sin theta is equal to e to the power minus I theta. Is it or not? Similarly, here we can write cos of pi by 2 minus I into sin of pi by 2. So cos of pi by 2 is 0 and sin of pi by 2 is 1. So finally what is the answer I am getting? That is minus I. So z bar into omega, which I am getting, that is z bar is into omega is equal to minus I. This is your answer. I hope this is clear to all of you guys. Understood or not? This is the question came in 2019 JEE mains. Is there any doubt you can ask? If you have any doubt, you can ask in this question. I hope it is clear to all. We use the previous properties of argument conjugate modulus and we solve the question. Is it or not? Is there any doubt? You can ask. Otherwise, thank you all, and it's end of your class. It's time now to end the class here. Thank you all. Thanks to everyone. Thanks for your time. Bye bye. Take care, everyone, guys. See you in the next class.